Welcome to Reducing Embodied Carbon Meeting CI with Biomass Graphite Polystyrene EIFS. This course explores how to improve the performance and sustainability of buildings by incorporating exterior insulation and finish systems with biomass graphite polystyrene insulation. This course is sponsored by BASF. This presentation is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the presentation without the written permission of BASF is prohibited. This learning program is registered with AIA CES for continuing professional education. As such, it does not include content that may be deemed or construed to be an approved or endorsement by the AIA of any material of construction or any method or manner of handling, using, distributing, or dealing in any material or product. AIA CES has reviewed and approved AIA continuing education credits for this learning program. Learners must complete the entire learning program to receive continuing education credit. AIA continuing education learning units earned upon completion of this course will be reported to AIA CES for AIA members. Certificates of completion for AIA and non-AIA members are available upon request. This course explores how designers can reduce embodied and operational CO2 emissions through the use of graphite polystyrene exterior insulation finishing systems while satisfying the requirements for continuous insulation in new and retrofit projects. As an intermediate level course, participants are expected to be familiar with insulation alternatives and EIFS. Health, safety, and welfare credit justification. This course also dives into new processes using renewable and biomass feedstocks and making GPS that lower carbon intensity as verified by sustainability tools, including LCAs and EPDs. At the end of this program, you will understand what exterior insulation finish systems are, their history, and their component parts. You'll understand what the insulation alternatives are for these systems and the advantages of graphite polystyrene for EIFS. You'll be able to explain what continuous insulation is and how continuous insulation is mandated in building codes, and graphite polystyrene EIFS' role in reducing carbon emissions. You'll be able to understand and compare the embodied carbon of EIFS insulation by a better understanding of life cycle analysis and environmental product declarations. You will also know what biomass balance approach is and its role in reducing CO2 emissions of EIFS using graphite polystyrene. And you'll understand third-party tools to verify these claims. You'll also be able to access graphite polystyrene EIFS case studies and design resources and standards for specifying graphite polystyrene EIFS. There will be a number of different acronyms used in this program, so to just briefly go over what they are, first we have EIFS, which is Exterior Insulation and Finish or Finishing Systems. GPS is Graphite Polystyrene. EPS is Expanded Polystyrene. XPS is Extruded Polystyrene. PU is Polyurethane polyisocyanurate. SPF, Spray polyurethane foam. CI, continuous insulation. BMB, biomass balance approach. R value, resistance to heat flow, it's a measurement of insulating value. So, learning objective 1, what are EIFS? What are the history of EIFS? What are the insulation alternatives? And what are the advantages of graphite polystyrene? EIFS is an acronym for Exterior Insulation and Finish Systems. According to the International Building and Residential Codes and ASTM International, EIFS are a non-load-bearing exterior wall cladding system that consists of an insulation board attached adhesively or mechanically or both to the substrate, an integrally reinforced base coat, and a textured protective finish coat. EIFS serve several functions. First, as we stated, as a wall cladding, but also as continuous insulation and weather resistance. Components of EIFS include the finish, the mesh, the insulation, the adhesive, the substrate, and the stud. A brief history of EIFS. In 1951, EIFS was developed in Europe as a replacement for stucco after World War II and was initially used to repair stucco walls. They also significantly improved the energy efficiency of these buildings, provided effective moisture control, high durability, and weather resistance. In 1969, Francisco Morcelli, the founder of Graphite Systems, is the man who introduced exterior insulation and finish systems to North America. In 1969, Graphite set up a shop in Rhode Island and brought the technology to the United States. During the 1970s and 80s, the American energy crisis drove demand for EIFS because, in addition to mimicking the look of stucco, EIFS also provided something we now refer to as continuous insulation. In the late 1980s, installation-related moisture problems, specifically in the residential sector, led to a series of lawsuits, and as a result, EIFS with drainage was introduced in 1996. And this innovation and improvement was so successful that in 2009, the International Code Council included EIFS with drainage into the code for both residential and commercial construction. From 2010 to present, some of the improvements and innovations include the inclusion of graphite polystyrene for exterior insulation finish systems, which increased the insulating value by as much as 25% while reducing the embodied CO2. EIFS insulation types include EPS, GPS, XPS, and mineral wool. But EPS-based insulation, which includes GPS or graphite-enhanced EPS, leads the market with a majority revenue share of about 20%, which is expected to increase to 30% by 2030. Now, the top reasons why EPS is the leading insulation for this market includes its lightweight characteristics. It's easy to handle, which reduces labor and time. It's durable and it's reliable. Here's a brief history of graphite polystyrene. It starts in 1951 when BASF patented EPS, or expanded polystyrene, as an insulation under the brand name Styropor. Then in 1997, the same company patented graphite polystyrene under the brand name Neopor, and this featured the inclusion of graphite, which increased the insulating value of between 20 and 25% over the white EPS. Then in 2009, BASF invents an extruded version of graphite polystyrene, which lowered the water absorption qualities, again with the same increase of R value of between 20 and 25% over the white EPS. Now, the reason it's between 20 and 25% is because the graphite polystyrene actually performs better in colder climates by as much as 5%. And then in 2024, BASF offers a biomass balance approach to manufacturing graphite polystyrene, which significantly lowers the embodied carbon of this material. To understand why graphite polystyrene works, first, we know that warm air always moves towards cold air, and while no insulation completely stops this heat transfer, it does slow it down. So if we take a look at EPS, it works because it creates tiny air pockets within each bead when formed, which traps the air into these pockets and slows the movement towards cooler air. Graphite EPS works this way too, but it uses the power of graphite's reflectivity to increase the insulating power. As radiant heat moves through the graphite-enhanced material, it's reflected hundreds of times, significantly slowing down this transfer. The result is increased energy efficiency. Another way of looking at it is by visualizing a person walking in a straight path from point A to point B. Walking in a straight line, like traditional EPS, would be much faster than in a path that took many twists and turns along the way, like GPS. Graphite improves the overall performance of EPS in several important ways. Graphite is the most stable form of carbon and is a completely safe substance that doesn't react with other chemicals or off-gas in the building. It increases the insulating value by about 25% over white EPS via its ability to reduce thermal conductivity and reflect radiant heat with no thermal drift. It also has nominal water absorption, is 100% recyclable, and adheres to the same ASTM standards as traditional EPS and XPS and other main polystyrene-based foams. However, its performance characteristics are different enough that the main specification tools in the AEC industry in North America have created an entirely new graphite polystyrene category to help product specifiers identify its characteristics. It also has the lowest embodied carbon of all plastic foams in North America. Through LCA and product-specific EPDs, GPS has proven to display lower embodied carbon than any other rigid foam insulations in North America, including EPS, XPS, polyiso, and mineral wool. It uses 30% less material mass than XPS for the same R value. It also offers 20 to 25% more insulating value than EPS at the same thickness. Time for a little pulse check, just to make sure some of this information is sticking. I bet it all has, but just in case, here's a question. What are the functional advantages of graphite polystyrene insulation over white insulation EPS, or expanded polystyrene? Choice 1, number 1, higher R value and lower embodied carbon. Number 2, increased design flexibility. And number 3, there are none. They perform exactly the same way. If you answered number 1, higher R value and lower embodied carbon, you got it. Moving on to learning objective 2, explain the importance of continuous insulation, define what continuous insulation is, its role in building codes, the need for continuous insulation, and how graphite polystyrene EIFS provides continuous insulation, and its role in reducing carbon emissions, both embodied carbon and operational carbon emissions. Continuous insulation defined. Continuous insulation is insulation that runs continuously over structural members and is free of significant thermal bridging. such as rigid foam insulation above the ceiling deck. It is installed on the interior, exterior, or is integral to any opaque surface of the building envelope. So, why do we need continuous insulation? We need continuous insulation as a strategy to reduce CO2 emissions which are caused by heating and cooling our buildings. Now, CO2 is a heat trapping gas, or we often refer to it as a greenhouse gas, which occurs from the extraction and burning of fossil fuels such as coal or oil or natural gas, and from natural processes like wildfires. But since the 18th century, human activities have increased CO2 in the atmosphere by 50%. NOAA has reported global atmospheric CO2 was increasing at a rapid rate and got a new record high between 2021 and 2022 by 2 parts per million in that 1 year. And so this is much more than occurs naturally. And so what are some of the results of this increased carbon in the atmosphere? Well, we see loss of sea ice, sea level rise, heat waves, crop seasons are changing, drought, wildfires, species extinction, displaced habitats, acidification, and more. So we want to eliminate that heat loss, or energy loss rather, and we do that one way is through continuous insulation. Well, exactly what it does is it eliminates something called thermal bridging. And so thermal bridging is where we see the framing elements here in the top picture in yellow, and the bottom picture in yellow, and the residential example, the commercial example below. In fact, if we can eliminate most of that thermal bridging, we can save between 20 and 70% of the energy flow through the building and walls. And so that's significant. A majority of EIFS are in commercial buildings where they play a pivotal role in this way, decreasing energy consumption. And the non-residential segment accounted for the largest revenue share of more than 57% of the EIFS market. But certainly there are a lot of homes in this country that are clad with EIFS. EIFS achieves a 50% energy savings for both commercial and residential buildings over typical materials that might be used. This is a statistic that is referenced by the U.S. Department of Energy. So the point is, continuous insulation eliminates thermal bridging, and that saves energy. So EIFS helps meet continuous insulation requirements that are required by many building codes and standards, including the 2021 IECC, ASHRAE 90.1, California Title 21, and other state programs, as well as stretch codes that have been adopted in cities like Portland, Oregon, Portland, Maine, Boston, New York City, to name a few. And the reason we're not including the 2024 IECC code here is because it's a little less rigorous than the 21 code, although it does call on a greater use of continuous insulation than 2019. Its lag in state code adoption. States take several years to adopt the new code. So more states have already adopted the 2021 code, and many state tax incentives are linked to the 2021 code. And so this is the reason why we kind of focus on the 2021 IECC as the standard. Continuous insulation requirements are called out in more stringent ways in both 21 and 2024, as I just said, for both residential and commercial codes. So here's a map that was updated in the fall of 2025, which shows the adoption of the energy codes. Because not all states have to adopt the most rigorous code, but you can see certainly that there are a lot of states that have, and regions and municipalities that have adopted the 2021 code. The 2021 IECC residential code now requires continuous insulation in almost all climate zones in a prescriptive pathway. And the commercial code, which is based on ASHRAE 90.1, has required continuous insulation for more than 30 years. The 2021 International Energy Conservation Code introduces more stringent requirements and greater emphasis on continuous insulation for commercial buildings, although, as I mentioned, that requirement for commercial buildings has been in existence for a number of years, decades. But however, the 2021 version actually increases the R values and the U factor requirements for roofs and above grade walls and below grade walls with more rigorous ASHRAE 90.1, 2016, and 2019 standards. So this is a significant increase over the IECC Commercial Code of 2019. Lastly, in addition to state and regional tax programs, there are voluntary building programs that require continuous insulation, including LEED, the National Green Building Standard, Living Building Challenge, Passive House Standard, and Earthcraft. It's time for another pulse check. Which of the following statements are true? Continuous insulation is insulation that wraps around the below-grade perimeter walls only and aids in reducing water intrusion. Number 2, continuous insulation runs continuously over structural members and is free of significant thermal breaks. Number 3, continuous insulation significantly reduces CO2 emissions by enhancing a building's energy efficiency and minimizing the need for heating and cooling systems. If you said number 2 and number 3, you are correct. On to learning objective 3. Moving right along. Compare the embodied carbon of standard EIFS insulation options through available life cycle or LCAs and environmental product declarations, which are EPDs. So let's look at it slightly differently from a life cycle perspective. So the process of comparing the embodied carbon of a material begins with developing a life cycle assessment. And for example, we can see cradle to gate, which is the production phase. It includes the extraction of the raw materials, the transportation of those materials to the manufacturing facility, and all the energy taken to actually manufacture that material. And then we have the construction process, which includes transportation to the actual construction site, and everything that happens during that stage, the use phase, end of life stage, and recycling stage. So when we talk about measuring embodied CO2, what we're really talking about is the production phase. So it is the production phase where we are actually measuring the energy used to manufacture that material. That is called the embodied CO2 of the material. Life cycle analysis are long and difficult to use on a daily basis. So the industry creates something called environmental product declarations, which are short form LCAs. In fact, they were first used in Sweden in 1997 as sustainability decision-making tools. And they're based on the life cycle analysis, but they also use something called product category rules so that we can compare similar products that use the same functional unit. For example, foam sheathing insulation. And so we are able to compare apples to apples along similar products. But we also have to compare the same life cycle scope. So there are EPDs that might measure the a cradle to gate, which is the manufacturing process, and extraction, which we discussed. That's where embodied carbon resides, or there might be an EPD that considers all of the life cycle scopes. So that's something that can also be considered. There are different types of environmental product declarations, including individual product types or manufacturer types or industry-wide types, supply chain types, etc. Here's a way in which one firm, KPMG Architects, actually used EPDs to assess a number of different environmental attributes, including embodied carbon. For common insulation types, we have taken their findings and extracted out the types of insulation materials that are commonly used in EIFS to compare and contrast. So the conclusion is for EIFS insulation, the graphite polystyrene, which is manufactured using something called biomass balance approach, has the lowest embodied carbon of all of the common EIFS insulation materials used in the study using their available environmental product declarations. Graphite polystyrene for EIFS offers more R value with less embodied carbon. So we know through life cycle analysis and product-specific EPDs, GPS has displayed lower embodied carbon than any other rigid insulation board in North America, including EPS, XPS, polyiso, and mineral wool, because it uses 30% less material mass than, let's say, XPS for the same insulating value or R value. It also offers up 25% more insulating value than EPS at the same thickness. So less density, more insulation value equates to less material and a lighter carbon footprint. So this just makes sense. GPS is in its own specific category in the design tools that you may be using, termed graphite polystyrene. However, it adheres to the same ASTM standards as EPS and XPS and other main polystyrene-based foams. And this ASTM standard is ASTM C578, by the way. However, its environmental performance characteristics are different enough that the design community, using these specific tools, for example, BSD SpecLink or MasterSpec, they've assigned graphite polystyrene its own category to help product specifiers identify its attributes and specify it. Okay, we're in the home stretch. That was a big section, I know. But it's time for another pulse check. So take a deep breath, maybe do a little stretching, and ask yourself the following. Embodied carbon, which is cradle to gate, includes which of the following of the product's life cycle? Number 1, production, which includes raw material extraction, transportation to the manufacturing site and the manufacturing. Or 2, the production phase, the building construction phase, and the building use phase. Number 3, the production phase, the building construction phase, the building use phase, the building end-of-life phase, including deconstruction. If you said number 1, production, raw material, transportation to manufacturing, and manufacturing, that's the correct answer. Learning Objective 4. Know what the biomass balance approach to manufacturing is and how it is currently reducing the CO2 footprint of GPS and associated EIFS systems. The biomass balance approach is a chain of custody model that tracks renewable, plant-based materials as they are mixed with fossil-based materials in the production process. This method allows for the gradual transition of bio-based feedstocks in existing systems without changing production processes as the renewable raw material is attributed to specific products at the end of the supply chain through an independently certified method. The resulting products are chemically identical to the fossil-based counterparts, but have a lower carbon footprint. This enables companies to meet their sustainability goals while not sacrificing any of the performance characteristics of the final products. In fact, by using this approach, manufacturers can reduce their embedded emissions for graphite polystyrene insulation board by as much as 90% when compared to traditional fossil fuel feedstock methods. Okay, so moving on to Learning Objective 5. Access case studies, design resources, and standards that help designers specify lower embodied CO2 graphite polystyrene EIFS. So what would the specification look like? Well, here's an example of a Sika Corp exterior cladding system which uses graphite polystyrene and EIFS. And they call for a maximum 12-inch thickness of graphite polystyrene type 1 rigid insulation board with a maximum 7.8-inch thickness of graphite polystyrene plus type 2 rigid insulation board. And so they really, in their Platinum CI system, they will tell you exactly what to use and what to specify. So if you don't know where to start, we're going to give you some resources on where you can look at some interesting specifications and projects as well. For example, this project, again, it's a Sika Core project. It's a commercial case study. It was located on the waterfront in New Jersey. It's called The Wave. It's a mixed-use luxury building with uninterrupted views of the Manhattan skyline. It's 24 stories high. It's both retail, again, it's mixed use, so it's got residential and retail spaces, and it's got this really cool wave-like surroundings. So the building exterior is, in fact, the Platinum CI wall system, which is exterior insulation finishing system with a continuous drainage. And so you can see also, the Neopor rigid board insulation enhances the R value and impact resistance. And also EIFS, I'm sure many of you already know the design flexibility of EIFS is extraordinary, which is one of the reasons why the designers were able to create this really interesting profile. So here's some design resources and carbon calculators and plugins that you may already be using, which will help you select, compare and contrast different rigid board insulations when you are designing with EIFS or other projects. So the EC3 tool also has its own standalone platform, but it has plugins, and that help basically feed the TallyCat plugin, a Procure plugin, Rib and SpecLink, and so. But there are other design platforms that have their own calculators, including BIM Smith, MasterSpec, Atrius, etc., Sustainable Minds, and Climate Action's Beam. So all of these calculators can really help you, as I said, compare and contrast and plug in what it is you need to do, and then take a look at the environmental impacts across the same product category. For example, you can compare global warming potential of rigid foam sheathing materials. And here's going right to EC3 tool, which is an open source platform. So it's free to use, and it's pretty impressive. So here's an example of the tool, and which you can use without going through any of the third-party plugins. And it gives you basically a comparison of the global warming potential of in this case, type 1 rigid foam board insulation. Safety standards and resources regarding EIFS are important for you to know about, EIFS with drainage and the fire resistance of these systems, and also for graphite polystyrene in general. So here are some resources for you. Here's an ANSI standard for exterior insulation finish systems and EIFS with drainage. And these are all downloadable links that you will get when you download the PDF of this presentation. The National Fire Protection Association, or NFPA, NFPA 285. And that's the standard fire test method for evaluating the fire promulgation characteristics of exterior wall assemblies containing combustible components. And you can see on and on. So these organizations, including ANSI, ASTM, UL, develop, publish, and periodically update standards that you will want to take advantage of. And EMA, the organization EMA, represents the EIFS organization, or EIFS industry in general, and they will always have really good information for free at ema.org. When specifying graphite polystyrene for EIFS, make sure to specify those that have third-party certified standards and testing. For example, Green Guard Gold, or the Collaborative for High Performance Schools, CHIPS, and the companies and product-specific EPDs that you'll be wanting to look for will have a reputable EPD provider or LCA provider, including NSF, the Sustainability Consortium, UL. Additionally, here are some links to additional resources that you may want to have, and please feel free to download this presentation where you will find all of these links, including a link to the specification on the neopor.basf.us website. Thank you again for joining us. This presentation was sponsored by BASF.